Okay, so the purpose of this little video is to help be a supplemental explanation of how we use Excel and how we're going to do most of the calculations for the equilibrium lab that has just been posted. Well, I've been posted a little while ago. So I'm going to screen share and go straight to Excel. So the first thing we want to go as we look at Excel is how do we use Excel? Excel is an incredibly powerful tool if you learn just a bit about writing equations. These will not give you any of the actual numbers you need for the lab, but it'll teach you a bit. The first thing we need to know is how to write an equation. Whenever you're using Excel as a calculator, we always start off with equal sign. Equal sign will allow you to say, this box will equal whatever I type in next. So if I'm typing in 3 asterisks, which is the time sign, 5 divided by, which is the backslash or front slash, whatever this slash is, 10, it's going to say 3 times 5 is 15 divided by 10. Do an order of operations, so 1.5. Now, if you want to choose then, say, do some math, and instead of typing in the number, we can refer to a box. We can say equals the number 3 asterisks, and I just click and select this box, and it will say box A2. And so it'll say whatever number is in box A2, I'm going to multiply that by 3. And that's the basics of how you write any mathematical thing. If I wanted to say then take that number and raise it to the power of 2, so square it, I can say caret 2. That will square this. If I did caret 3, it will cube it. Now, if I wanted to square root, I can either type in SQRT, and it'll give you some options. It says returns the square root of a number. I put parentheses, and so notice it says number. So whatever number is in these parentheses will get square rooted. Click A4, in parentheses. You always need to remember to end all parentheses you start, or else it will tell you there is an error. And so that gets it back. The alternative way would have been equals this raised to the power of 1/2, which is also the same as a square root. But there's a lot of different functions in here, including averages and standard deviations and all sorts of great things. So let's work with, we'll say the iron concentration is 3.5 E negative 3. Now, you'll notice, so this is that capital E is telling it times 10 to whatever the power comes after it. So if you look up here in this function box, it says 0.0035, which is 3.5 times 10 to the negative third, which is what we read right here, 3.50 E negative 3. So that's why you often see me using the capital E's, because my mind is working on Excel time. Now, as we go through boxes, there are some cool things you can do, including dragging down functions, dragging down repetitious things. So like, for example, look, we have 5 test tubes we need to look through. I highlight those, but I only wrote down test tube 1 and 2. If I highlight those 2, we can get it to repeat a pattern. So if I go down to here, the corner where that little dot turns to a plus, I can now drag this down, and it will keep repeating the pattern of increasing by 1, 2, 3, 4, 5. Now, with this in mind, the concentration. The concentration for these 3 test tubes is always going to be equal to our starting concentration times the amount of iron we used, which is, depending on the tube, divided by 10. And you'll have a little problem here. If I drag this down, what? All these are 0. What's the matter? Well, the matter is, you notice as I click here, this is A2 times D2 divided by 10. One says A3 times D3 divided by 10. Well, there's nothing in A3, which is why it becomes 0. So how do I handle that? Well, you could either type in the direct number, or in this original equation, you set this so it always refers to A2 and doesn't change when I drag this down. So the next thing I need to show you is the always sign, and that is a $sign on the keyboard. When you type $A, $2, it means as I drag down this function, it will always keep box A, box 2. So I drag this down, suddenly we have, 3.5, it doubled, it tripled, it quadrupled, it pentupled. It's changed by that amount. So notice like always A2 times D2, which is 1, divided by 10. Always A2 times D3 divided by 10. So on and so forth. That is a very important thing to keep in mind. Now the absorbance. So like I'm making up numbers. So this may be garbage. So 5, 2, point. Okay, so we got some numbers. So the next step, so the first thing you want to do in the lab, once you find out your initial concentration of iron. So remember, we took the iron, we diluted. So we changed the concentration of iron by a certain factor, and we had the dilute iron, and that was used in this step. So we have to figure out what is the concentration of iron in each test tube. And because iron is the limiting reactant and the thiocyanate is in such excess, we make the standard assumption that all of the iron is consumed and turned into iron thiocyanate. So we're going to graph the concentration of iron thiocyanate versus absorption to get a standard, the standard curve. So I'm going to insert a graph. As we insert a graph, we are going to always use the scatter. We do not want to auto draw the line. So we draw it here. We're going to right click this. We're going to add a trend line. It's always going to want to be a linear trend line. And never set the intercept to 0, but always just by the equation, play the r squared. R squared value tells you how well does this line fit the data you have. The closer this is to 1, the better your data fits. So your y equals 106.29 minus 0.0074. So 106.29 negative 0.0074. So there is your molar absorptivity of iron thiocyanate and your y-intercept, which is like an error that would be brought on by your instrument. So with that in mind, the next thing, what we did was we varied the amount of iron and we varied the amount of thiocyanate. And we looked at the absorbance. So let's say some value is 0.04048, 0.035, well, 0.062, 0.064, 0.0 0.73, 0.088. So T1, T2, T3, T4, T5. Absorb. I'm just putting hypothetical numbers. These are just so we can have something. Okay. So hypothetically, we have the iron and the thiocyanate, and we have the absorbance. So the first thing we need to find out is our thiocyanate concentration. So what do we have to do? Well, the thiocyanate concentration is equal to the X in that equation. If we have an absorbance, we can get our thiocyanate. So we have to solve this backwards. We have the Y. Now we need to solve for the X. So for this, we'll take our absorbance. Would add in our Y value to get that to the other side. So you got to flip that to the other side, and then we'll divide by our slope. That would give us the concentration of iron, thiocyanate. So that should make sense. This is 5.21 times 10 to the negative fourth, and that absorbance is somewhere between 1 and 2. The absorbance of 1 and 2, and so the concentration is somewhere between 1 and 2. Now here's where we have to think a little bit harder. We have an ICE table, I, C, E. We have our iron, we have our thiocyanate, and we have our FeSCN, our iron thiocyanate. Well, at I, well, we have our concentrations at I. Copy, paste special. Okay. And at initial, this would be 0. At change, it's going to be minus x plus x. Oh, no, plus x. Let's just keep those as not in general, but a name, so you can see those. Those aren't numbers, those are just, okay, no, don't want that. Text. X plus x. Okay. So with that in mind, we have to add, okay, with that in mind, we now have the equilibrium concentration of iron thiocyanate at that situation. It's right there, because the reaction happens and we form that much iron thiocyanate. So that is our X. With that in mind, how do we find our iron concentration and our thiocyanate concentration at equilibrium? Well, it's going to be I plus C. So equals whatever this number is plus C, which is a negative X. So negative X. So we have, 1.79. So we've lost some of this. And what is this? Well, we take this and we plus our c, which is our negative x. We have our value. So then finally, once you have every value at equilibrium, then you can find K. Remember, K is products over reactants. There's our product. There's our two reactants. So what do we have to do? We have to say equals our product concentration divided by our two reactant concentrations. And in this case, oh, I got 977. Now, with that in mind, you repeat this 4 more times. And then once you have 4 more values, you can take the average K. To do that, you just type equals average, parentheses, and then you highlight all the blocks you want to look at the average of, and parentheses. And it will calculate it. Because there's no answers, there is no, it's averaging out of 1. As soon as I get a second one, say that's 850, you take the average out of 2. 895, 3, 984, and so on and so forth. So if you are clever and you write this in an equation format so that you get a different iron thiocyanate, and you use the same equation for this, so it's referencing the correct boxes, what you can end up doing is when you drag these down, when I drag these down, it's gonna do all the boxes correctly. Do all the boxes correctly and calculate all of our numbers. And so you can do that all at once rather than type it in, do it again, type it in, do it again. So if you got that, you understand that this lab will become a lot easier. But if not, it shouldn't take too long. This lab took a while to do, but thankfully, all that is done for you. So hopefully this will help you, introduce you to Excel, work this out, and show you how you do some of the calculations. Essentially, the iron thiocyanate, the thing we actually measured, is at equilibrium. The initial concentrations can be found using M1V1 equals M2V2. We know the initial concentrations from the bottles. We know the volume we used, and we know the total volume in the solution. So we can find what is the concentration of each one in each test tube. And those concentrations are considered the initial points. So we got everything we need to do this lab. So hopefully this has been helpful. I wish you good luck, and if you have any more questions, just send them on.